In this session, we will discuss about the continuous probability distributions. First, when we are considering about the continuous probability distribution, and when we are discussing about the probability distribution, we have mainly divide these probability distributions. If you are having the probability distributions, we have divided it into two parts. First one is based on the type of the variable, it is discrete or else it is the continuous. Therefore, in the previous session, previous sessions, we have finished discussing about the discrete distributions. Under that, we have discussed first about the Bernoulli trial. Thereafter, we have discussed the binomial distribution, and thereafter we have discussed the Poisson distribution. Now we will going to discuss about this continuous probability distribution. Therefore, when you are going to have an idea regarding the underlying probability distribution, then we can use this concept of this continuous probability distribution in the case where our variable is a continuous random variable. Suppose that we are having a continuous random variable, then we can say that this follows a continuous probability distribution. If you are trying to identify the associated probability with this continuous random variable, then we can have our continuous random variable as x, and then we can create the probability of x, that x equals x, or in this way for a continuous probability distribution. And when we are discussing about the continuous probability distribution, and here just part of this example is included, but here we are considering about this example. Suppose a researcher is interested about the time spent in a shopping mall by a customer. Suppose that here we are going to worry about the time that a customer spends inside the shopping mall. When we are going to discuss about, or when we are going to have an idea regarding the time that the customer is spending, actually we are having, or we are interested in the time. Therefore, the time spent will be our random variable. But once you consider about this random variable, it is quite what we can say, the time spent, actually the time is a continuous what we can say is, as we are measuring the time in a continuous scale. Therefore, we can say that simply this time is a continuous random variable. Therefore, we can say that time spent can be categorized as a continuous random variable. Therefore, if you are considering about the probabilities of spending that much of time, and if you tabulate it, then you can simply obtain a continuous probability distribution. When we are going to look about this continuous probability distributions, here we are going to discuss about the two special cases. It is the normal distribution, and then we will discuss about the exponential distribution. But in this session, I will just limit it to the discussion of the normal distribution, and by my next session, I will discuss about the exponential distribution. Therefore, first we will have an idea regarding the normal distribution. Okay, this is the first distribution that we are going to discuss under this continuous probability distribution. It is the normal distribution. And here I have just included some details regarding this normal distribution. And if I go through them, this normal distribution is a continuous probability distribution. Since it is a continuous probability distribution, we are discussing it under this section. And then this normal probability distribution is formed up using a normal random variable. Here, apart from saying it as a continuous random variable, we tend to say it as the normal random variable. It is because this is a special case. Our continuous random variable can be behave as this normal random variable. We are saying that if the continuous random variable follows the normality properties, then we can consider such random variable as a normal random variable. And when we are considering about these normal distributions or this continuous distribution, this normal distribution is the most versatile distribution that we are considering for this continuous probability distribution. And this normal probability distribution is frequently using probability distribution, and for almost all the types of data driven experiments we can use this normal distribution. And in the fields of the agriculture, medicine, trades, business, and any industries, we are applying this normal distribution. It is because generally we are dealing with the large scale of data. Therefore, most of the time we can identify that the data follows these normality properties. Therefore, in that situations, we can apply these normal distributions. And we can say that the normal distribution can be used to characterize the uncertain in a variety of the real world process to make the statistical inference and to approximate the other probability distribution. In the last two sessions, I have just mentioned about this part, approximate other probability distribution. It is quite like if you are having a binomial distribution, I told you that we can approximate it to the normal distribution, as well as for the Poisson distribution also, we had an normal approximation. Therefore, when we are going to discuss about some other distributions also, we can approximate it by this normal probability distribution. And the next thing is, if you are going for the statistical inferencing, then for the statistical inferencing also, the normal distribution is the widely using technique. Therefore, we can say that the normal distribution can be approximated for a large number of random variables that occur in practice. Therefore, apart from the other probability distributions, if you are considering the random variables, we can assume these by assuming and by checking the properties of this normal distribution and to be a normal random variable. We can approximate such variables also using the normal distribution. Therefore, here also I have mentioned again that this statistical inferencing process, therefore, for the statistical inferencing process in almost all, or we can say it as the many real life situations, we can use this normal probability distribution. And limited data is a subset of the total amount of information available about the process. And then it is discovered that the normal distribution can be used to characteristic the sample distribution of many sample statistics, regardless of how the entire body of data is distributed. It is because suppose that in generally we are not going to have the entire population for our studies. Therefore, if you are having the large populations, what we tend to do is we are just trying to obtain a small sample from this data, and we tend to perform the statistical analysis for the sample, and based on the output or based on the results that we are obtaining, we can inference about the population as well. But when we are having the sample, therefore it says that regardless of the population's distribution, we can use the sample in the normal distribution. If the sample follows the normality properties, then again we can, with the regardless of the distribution of the population, we can comment about the population based on this sample data. Therefore, where this concept will be much more helpful. It is because actually we do not know that we cannot collect all the data from the population. Therefore, in such situations, for the statistical inferencing, we can use the sample data. And the next thing is, we are assuming that if the sample follows the normality, then population itself also follows the normality. It is the general concept that we are used in the analyzing of the data based on this normality distribution. And the next important thing is most of the powerful tests are based on these normality assumptions. Therefore, once the normality assumptions are not violated, or it has fulfilled, then we can apply such this higher order or the powerful test or significant test to test for the statistical analysis. But if those assumptions are violated, then we have to use some less powerful test, what we are saying as the non-parametric tests. And now if we are here, I have discussed about the importance of the normal distribution, and now we will just look about this background. The normal distribution is a bell-shaped distribution. It is quite like we say it as a bell-shaped distribution because of its shape. It is because the less number of data at the endpoints. Here we can say it as two ends. We will have less number of data, and for the middle of the series we may have large number of data. Therefore, for the left hand side as well as for the right hand side, we may have two tails. Therefore, now if you see about its shape, it is quite like a bell. That is why we are say that normal distribution is a bell-shaped distribution. And this distribution is often called as the Gaussian distribution as well. It is because for the um, for have the it is because the person who lived in the period of 1777 to 1855 has done much more work on the formula for this normal distribution for this the Carl Friedrich Gauss. Therefore, that is why we are say this distribution as the Gaussian distribution as well. Rather than saying it as bell-shaped distribution, commonly we are using the terms as the normal distribution and the Gaussian distribution to name this normal distribution. Okay, now we will move for the statistical concept of this normal distribution. Suppose that x is a random variable for the experiment, and suppose that x follows a normal distribution. It in the sense it follows the normality condition. That is why we can say that the random variable x is following a normal distribution. When we are going to discuss about the normal distribution, here we are interested in two parameters. In the previous cases also, in the previous sessions, we have discussed that for the Bernoulli, we are having the only one parameter as the probability, successive probability. And for the binomial, we had two parameters. It is as the number of trials and the success probability. And for the Poisson, we had again one parameter as a rate parameter. Therefore, in the similar way, if you are considering about the normal distributions, here we may have the two parameters and we are naming them as the mean and the variance for the distribution. Therefore, based on the mean and the variance, which are denoted by the mu and sigma squared, we are writing down the formula for the normal probability distribution. Here I told you that the normal probability distribution is actually based on two parameters. Therefore, we can denote the normal probability distribution in this way. Here we can say that x, and this tilde notation says that it follows. Therefore, we can say that x follows a normal distribution. To represent the normal distribution, we write it as the letter n, and we are now writing two parameters. It is mu and the sigma square. Therefore, we can say that x follows a normal distribution having mean mu and the variance sigma squared. Here we are using the variance, not the standard deviation. Therefore, we have to use the sigma squared value. If you are having this notation, this x follows a normal distribution having mean mu and variance sigma squared, then we can write down the probability density function or the probability distribution function for the normal distribution in this form. It is written as fx. It is quite, it says as the probability that x equals to x for a single point. Then we can say it as the fx We can obtain this probability by using the equation. It is 1 over square root of 2 phi sigma squared multiplied by exponential or e to the power minus half times x minus mu divided by sigma to the power 2. And some people are try to or used to write it in this way as well. It is 1 root 2 5 sigma squared into e to the power minus 1 over 2 sigma squared x minus mu squared. Therefore, this is just the expansion, just taking the sigma squared out of the bracket and just the remaining part writing in this way. Both these ways are correct, but I will try to limited my writing into this way. It is because this x minus mu divided by sigma quantity will be again interpreted in the another way. Therefore, if you are using this form, then it will be easier for our calculations. Now we will look about the properties of the normal distribution. We can say that the normal curve in the sense it is the normal curve. Here we can say this as a curve. Therefore, we say it as the bell-shaped distribution, and we are saying this curve as the normal curve. Therefore, we can say that the normal curve is not just one curve that represent a single continuous distribution. Therefore, actually there is, we can say it as a family of curves. When we are going to discuss about the normal distribution, we can say actually it as a family of curves. It is because if you are having a normal distribution, one may have the normal distribution in this form. And another one may say have the normal distribution in this form. Another may have the normal distribution in this form. Therefore, this is actually a family of curves. Therefore, no one can say that this is the only curve we are getting for the normal distribution. Therefore, according to the value of mu and sigma squared, based on the value of the mu and sigma squared, we may have the family of curves for this normal probability distribution. Therefore, this is what the first property of the normal distribution. Therefore, we can have it as sometimes we may have the very wider distributions. It is quite in this way. We may have the probability distributions in this way. Here also we may get this as a bell-shaped distribution. But in some scenarios, we may get our probability distribution. It is very narrow. And some other situations, it is quite in this way as well. Therefore, it is totally based on the values that we are getting for the mu and sigma squared. Therefore, the probability density function includes those two parameters. It is because E is the base of the natural logarithm and all the others are just the it can be say as the constant values. Even though this x is a variable, at a single time, if you are considering a single point or a single time, we are having a constant value at that time. But if you are considering it for the entire what we can say is that the entire experiment, it will be vary, but for a single instant it will be a constant. Therefore, the only varying parameters will be mu and the sigma only. Therefore, based on the value of mu and sigma squared, we may have the different shapes for the normal distribution, and that is why we can say that this is actually a group of curves. Then we are saying that the normal curve has a bell shape and it is symmetric around its mean. This is the next important property. If you are considering the normal distribution, I told you that it is a bell-shaped distribution, and if you consider about the midpoint of this distribution, now you can see that there are two sides, left-hand side from this value, and for these dashes, the right-hand side, we can say that it is the bell-shaped distribution is symmetric, and the value that it is divided into two parts is supposed to be the value as mu. Therefore, we can say that if you are folding the normal curve by the mean value, then you are getting two equal sides. Therefore, if you are considering about these two equal sides, we can say that the area in the left hand side of this curve will be equal to area of the right hand side of this equation. Therefore, this is the widely used technique for the calculations for the normal distribution. Therefore, we are saying that the normal curve is bell-shaped and it is symmetric around its mean. Therefore, the half of the area falls in the left-hand side from the mean and other half falls into the right-hand side of the mean. Therefore, in the case of a normal distribution, the perfect symmetry, when we are going to discuss about the symmetry, for the symmetricity, we are saying that this mean, median, and mode will be coincide. It is because it is here. If you are having the exactly symmetric normal distribution, then I told you that at this point it divides into two parts and it is symmetric around its mean. Then we can say that this mu, it will be same for, it is for the value for mean, and the value that we are getting for the mode and the value that you are getting for the median will be, you are getting the same value for all three instances. If you are calculating mean, median, or the mode, you may get the same values. And if you the next property, as we move away from the mean, it get closer to x-axis, the height of the normal curve is gradually decreases. Now you can see that it is a bell-shaped distribution. I have explained this previously as well. Now you can see that at the ends, at the right end and the left end, you can see that the curve is very closer to very closer to the x-axis. But if you are considering about the mean value, it is much more deviated from the x-axis. Therefore, this is the next property that we can identify in the normal distribution. As we are getting away from the mean value, it means that you are going to the end points of these endpoints for the x-axis. It means for the left side or this right hand side, then we may get our curve which is very closer to 0. But never we are saying that it touches the x-axis. It is because this is the next property at the infinity, plus infinity and minus infinity, we can say that x-axis and the curve will be touched. Or else for any other instances, we may get this normal curve and the x-axis very closer to each other, but they are not meeting in the anywhere apart from the infinity. Therefore, that is what I have mentioned here. The theoretically, the normal curve never touches the horizontal axis, extends to infinity on both sides. Therefore, that curve is asymptotic to the x-axis. That is what I have discussed previously as well. At the infinity, we are saying that x-axis and the curve touches each other. But apart from the infinity, we are not getting this touching of the axis and the curve before the infinity. And if you are considering about the normal curve, it is actually the curtices is equal to 0. It is not, we are saying that the curtices of the normal curve is 0. It is because in the previous sessions we have discussed about the leptokurtic and the mesokurtic. It is actually the peakness of the curves. Therefore, if you are considering about the peakness, then you may get very high peaks like this, or else very low peaks in this way. But if you are considering about the normal distribution, you may get its curve as this way. It is neither no sharp peak or neither no flatty peak like this. Therefore, it is having an average peak. That is why we are saying that curtices is 0 for the normal curve. And when we are discussing about the very first property of the normal distribution, it is supposed that the normal curve is not only one curve, it is a combination, or it can be considered as a family of curves. It is because based on the value of the mu and sigma squared, we are getting several curves for the normal distribution. Therefore, to avoid that cases for the calculations, what we are going to do is we are going to introduce a new probability distribution as the standard normal probability distribution. Actually, this is just an extension, or it is just derived from the normal distribution. Actually, this standard normal distribution is derived from the normal distribution. If you are considering about the normal distribution, suppose that if x follows a normal distribution, then it has the parameters mu and sigma square. This mu and sigma square can be take any values, but if you consider about the standard normal distribution, then this follows the value as the normal distribution having mean 0 and sigma as 1. Therefore, if our distribution has the mean 0 and variance as 1, then we say that it follows a standard normal distribution, and therefore we are writing the variable as z. Apart from writing x, we are writing the standard normal variable as z, and it says that z follows the standard normal distribution. Apart from writing standard normal, we are saying it as normal distribution having mean 0 and the variance as 1. Therefore, this is actually a special case of the normal distribution, and we are widely using this concept for in the calculations as well. Actually, we are trying to obtain this standard normal distribution. It is because for the easiness of calculation. Previously also I mentioned that this normal distribution is a collection of curves. It is actually a family of curves. Therefore, from when you are going to calculate the probabilities using this normal distribution, you may need curves or the probability values for each and every mu value and each and every sigma squared value. But avoid that confusion and this conflict, then we can use the standard normal distribution. And for the standard normal distribution, we are having a fixed value for mean and the variance. For the standard normal distribution, we are getting the mean as 0 and the variance as 1. Therefore, if you are going to find out the probability, so if you are going to do the calculations based on the normal distribution, what we are initially doing is we are trying to convert our normal distribution or transform our normal distribution into a standard normal distribution, and thereafter we are trying to perform our calculations based on this standard normal distribution. Therefore, if you say that if you are having the original variable as x, if you are having the original variable as x, then we can transform our original variable into a standardized variable. Therefore, this standardized variable is denoted by this z, and for this transformation, we can use the equation this z equals x minus mu divided by sigma. When I am explaining about the probability density function, I told you that instead of using x minus mu divided by sigma now, we can use the letter as z. Therefore, in some situations, if it is a standardized normal distribution, simply say about if it is a standardized normal distribution, standardized normal distribution, we may have the probability density function. It is fx equals to 1 over square root of, here we are getting 2 phi. Instead of sigma squared, we are using 1. That is why 1 times 2 phi gets the value as 2 phi. Then e to the power minus half, then x minus mu divided by sigma. Here, rather than saying it as x, we have to say it as z. Therefore, we can say it as it is x minus mu divided by sigma. Therefore, it's a squared term. Therefore, we can say it as writing as the z squared. It is z squared. But we are not going to use these functions for each and every calculation. Apart from using the functions, we tend to use the equation for the transformation, and then generally we are using the equation for the normal distribution for the calculations thereafter. Now we will see about the characteristics of the normal distribution. As the characteristics of the normal distribution, we can say that the probability density function or this PDF for the normal distribution, we have already discussed it. It is fx equals to 1 over root 25 sigma squared times e to the power minus half times x minus mu divided by sigma squared. Therefore, this is the probability density function that we are identifying for the normal distribution. And the cumulative density function, or what we are saying as the CDF, according to the theory of the CDF, we can say that this our function fx capital, we are using the uppercase letter f to denote the cumulative density function. Then if using the theory, we can say that probability of x less than or equal to x. Therefore, since this is a continuous probability distribution, instead of using the summation, we are using the integration technique. Here, when we are going to discuss about the normal distribution, I told you that it touches the x-axis at the minus infinity as well as it is from the plus infinity. Therefore, if this is less than or equal to value x, suppose that we are having the value x here, then all the values which are below the value x will be considered for the CDF. Therefore, we can have the integration from the minus infinity to the value x, and we are getting this as it is 25 sigma squared e to the power minus half times x minus mu divided by sigma squared dx. Using this integration, we can obtain the cumulative density function for the normal distribution. And the next characteristic we are going to explain is the expected value. The expected value for the normal distribution, it is denoted as Ex, and then using the same concept we have considered, we can obtain the expected value. In the previous sessions, we have used the summation. It is because we have discussed discrete probability distributions at that time. But once you come to the discussion of the continuous probability distribution, we may able to have the expected value using the, instead of using summation, here we have to use the integration from the minus infinity to plus infinity. We are using generally it as minus infinity to plus infinity because we do not know what is the exact lower limit and the exact upper limit on this case. Therefore, using this equation, it is x times fx dx, we can obtain the this expected value for the normal distribution as mu. This is the parameter value that we have used, the first parameter as mu. And the next thing is the variance, using the concept for the variance. Then we can use it for the x minus mu to the power 2 times fx, and we have to integrate it again from the minus infinity to plus infinity. Therefore, once you perform this calculation, you will get the variance for the normal distribution as sigma squared. We will discuss an example related to this normal distribution. Here, I have considered one example. The finance division of a company wishes to get an idea regarding the monthly overtime hours of the employee. Suppose that the finance division of a company needs to have an idea regarding the monthly overtime hours. Therefore, they have surveyed 200 employees of the company, and they have got the summary data in this way. Therefore, they have identified that this monthly overtime follows a normal distribution. Using the normal assumptions, they have identified that it follows a normal distribution, having the mean value of 35 hours and the standard deviation of 10 hours. Here they mentioned that mean with 35 hours and the standard deviation with 10 hours. Here you are asked to find out the probability that the employees having monthly overtime hours with these values. It is less than 40, less than 20, more than 60, and in between 30 and 50. Therefore, here I have included the solution as well. Therefore, now anyhow, I will do this calculation for you. Okay, according to this example, what we know is we are having 200 employees, and it follows a normal distribution having mean with 35 hours and standard with deviation with 10 hours. Therefore, first we'll try to write down all the necessary information. Therefore, what we are knowing is we know that we are having a if we suppose that uh, if we suppose that x is let be the uh, number of overtime hours, number of overtime hours that the employees having per month, and then it says that x follows a normal distribution, and we can say that x follows a normal distribution, and we need to identify the mean and the variance. Therefore, according to the given data, what we know is it is given as mean is 35. According to this data, it says that mean with 35 hours and standard deviation with 10 hours. Here they have not given us the variance. It is just the uh, standard deviation. Therefore, we can say that sigma is equal to 10. Therefore, what we need to do is if this is a normal distribution, the parameters we are having is mu and the sigma square. Therefore, to write down this normal distribution, this equation, what we need is we need the sigma squared as well. Therefore, using this sigma value, what we can do is we can write down the sigma squared as 100. Therefore, based on this value, then we can obtain the sigma squared is equal to 100. Therefore, we can write this as this x is the number of overtime hours per month, follows a normal distribution having the mean 35 and standard deviation as 100. Therefore, instead of 100, I will write it as 10 to the power 2. It is because now we can simply know that standard deviation is equal to 10. Then 10 to the power 2, or else if you need, you can write it as 100. In the first part, what they are asking is, what is the probability that the employee is having monthly overtime hours less than 40. Now we need to calculate this probability. In the first part, we need to calculate that the probability of number of overtime hours less than 40. When we are going to discuss about this continuous probability distribution, there is a concept called the we are not going to have it for these error corrections using this equality. Therefore, we are not going to have the corrections there. Therefore, even though we are having 40 or less than or 40, we are using the same concept. Therefore, what we can do is here, what we need to do is we need to identify what is the probability that x is less than 40. Therefore, according to the theory, if we are trying to do this according to the theory, what we need to do is we need to integrate the function. It is 1 over square root of 2 sigma squared times exponential, it is e to the power, then minus half times x minus mu square divided by sigma square dx, and it has to be integrate from minus infinity to 40. But this method is not easier method for us to do for each and every calculation. Therefore, apart from doing this lengthy calculation, what we can do is we can replace it using alternative method using a table. Therefore, we are not going to use this method for these calculations. Therefore, without using this integration technique, we are trying to use an alternative method. Therefore, first what we are going to do is here we are having the original distribution. Then we need to convert it to a standardized normal distribution. This is the normal distribution we are having. Therefore, what we are going to do is we are going to convert it into a standardized normal distribution. When you are going to convert this into a standardized normal distribution, what we know is if you are having the variable as x, we can convert this x to z using the equation z equals x minus mu divided by sigma. Using this equation, we can do the conversion or the transformation. Therefore, instead of x, now we need to replace the quantity. Therefore, what we are going to do is we are going to convert this x into z. This is the first step we are doing. Therefore, here what we are having is x, then if you subtract, okay, I will write it first. Here we are having 40. Then from the left hand side, I am subtracting mu. From the right hand side also, I am subtracting mu. But in the right hand side, we are having the numbers. Therefore, instead of mu, I can use it as 35. Then for the denominator, we are having the value as sigma. We are dividing this x minus mu by sigma. Therefore, we have to divide this by sigma. It means equal to 10. Now we have here it is p x minus mu divided by sigma. Therefore, we can consider it as value of z. Now this is the standardized transformation, and then we have to divide the we have to perform the calculation. Here it is 40 minus 35 divided by 10. You are getting this as 0.50. And when you are getting the answer at this point, please keep this into 2 decimal places. Always try to keep this into 2 decimal places. It is because it will be much more easier once you're going to read out this value from the table or the normal table. Therefore, always try to keep this value for 2 decimal places. Always we are taking it for 2 decimal places. Then we can now obtain this value by using the integration. But apart from using the integration, using the standardized normal, the PDF for the probability density function for standardized normal distribution, what we are attempting to use is we are using the critical values table for the standardized normal distribution. Therefore, here I have included the normal distribution table. But apart from reading the value, I will explain this as well. If you are having this probability of Z less than 0.50, actually we'll see what it means. Here we'll try to draw it. If you try to draw it, you will get it in this way. Here we are having the standardized normal distribution. And we know that it is symmetric around its mean. But we know that once you have do the transformation, we know that this standardized normal distribution having the mean value as 0. Now what we need to do is we need to find out the probability that Z less than this 0.5. Here we can consider it as Z less than or else Z less than or equal. It is because we are not going to worry about the continuity correction at this point. Therefore, we do not need to consider about whether even though it is less than or equal, we can use the same technique. Therefore, now we need to find out the probability that Z less than 0.5. 0.5 means you are having the value somewhat here. You may have the value 0.5 here. Then what you need to do is you need to find out the probability that falls into this region. Therefore, this is the area that we need to calculate, but we are not going to use the integration techniques. Therefore, apart from using the integration technique, we tend to use the standard normal table. Therefore, there are several types of standard normal tables you are getting, but you are getting this, we will be familiarized with this table. Here, this is the standardized normal table, which start from 0. Therefore, if I again write it here, then I will get this. If I draw the standard normal distribution, we can get the value from here. Value is 0. Then you know that from the left hand side and the right hand side of this standard normal distribution, you are getting the same area. Therefore, we are saying that the area under the normal curve is the probability we are getting. Since the maximum probability we are getting is 1, then what we can do is we can say that the area under this curve is equal to 1. Therefore, one part of this curve, therefore we can say that one part of this curve is equal to 0.5 and the right hand side part is also equal to 0.5. Therefore, if you are using this table, what we are getting is, if you are using this table, what we are getting is the probability. Using this standard normal distribution table, we are getting the probability of x less than or equal to particular value of x. Now this x is the value in the x-axis. Here, if you get the value as 0, you are getting this value as 0.5. That is how we are getting 0.5000 here. The probability value is given in this table with accurate to 4 decimal places. Therefore, this 0.5, we are getting it as 5000. Therefore, what we need to do now is, according to our calculation, what we need to find out is probability that Z less than 0.50. Therefore, now we need to identify 0.50 value. It is because we need to identify it on the x-axis. Here, we need to have where is this 0.50 value. Therefore, if I redraw this graph, redraw it, then I will get it in this way. This is the probability distribution I'm having, and here we are having the 0 value, and here somewhat here we will get the value as 0.50. Now we need to area in this region for the probability. Therefore, in using this table, we can take that the probability x less than or equal to, or this is here we'll take it as x less than or less than x less than x, particular value of x. Therefore, now we need to find out where is this 0.50. Now you can see that in the Z here in the first column it is given for the accurate to first decimal, and in the first row it mentioned the second decimal. Now we need to find out the value for 50. Then it is coming from this row, it is fifth row and the first column. It is because we can see that we are getting the 50 value. It is because first decimal is from 5. Therefore, we have to go from this row and then we have to come from this column. Now we can see that value is 0.6915. Therefore, now we need to identify the value is equal to 0.6915. Even though you have done the calculation using the integration techniques, again, you will get the same answer. Therefore, without going for this integration, what we can do is we can take this value is 0 is equal to 0.6915. It is the value mentioned here. You can see that value is 0.6915. Suppose that you need to calculate, it is actually apart from this calculation. Suppose that if you wish to find out this value, here if you take it is as 1.94. Suppose that if you ask to find out that probability is said less than 1.94, what we need to do is first we need to identify where is this value locates here 1.9, and then we have to find out for 1.9 it is somewhat here. Therefore we have to select the values in this row, and then 0.404 is here. Therefore we have to match the value at this point. Therefore that is why we are getting 9738 in this case. Therefore in this situation we'll get this as 0.9738. Therefore that is how we are using the standardized normal table to read out the probability values. Then in the second part of this calculation, it asks us, in the second part, it is asking that what is the probability that the overtime hours is less than 20, less than 20. Now, if you do the calculation for that as well, for the second part, we need to calculate that the probability of X less than 20. Here also what we need to do is first we need to convert this into the standardized normal distribution using the equation Z equals x minus mu over sigma. What we can do here is first we are writing it here, it is x less than 20, then minus mu, in the sense here we are getting 35 divided by sigma, here we are getting value as 10. Therefore once you perform this calculation, x minus mu over sigma, we can replace it by z. Then it is less than 20 minus 35 divided by 10. Here we are getting value as 0 minus 0.5. Since we need to keep it into two decimal places, therefore we can keep it in this way as minus 0.50. Okay, now we need to read out this probability of Z less than minus 0.50. If you draw it here, you will get it in this way. Here you may get, you will get the value as 0 here, then minus 0.5, minus 0.5. And you need to find out this probability value. But if you see about the table, you can see that it is starting from 0. But there are some other tables which is running from minus 3.99. Using such table, you can directly read out a value. But if you are getting a table in this way, you may not able to directly read out this value. It is because the table starts from 0, but we need to find out a value which is below than 0. Therefore, what we are going to do now is we are going to make some alteration for this inequality using the properties of the normal distribution. What we know is the normal distribution is symmetric around its mean. Therefore, what we can consider is instead of using this part, then we'll try to convert it into the right hand side of this mean value. Therefore, we'll get the mean value mean value, it is 0 is somewhat here. Now what we are doing is we are trying to obtain a similar image of this, or simply we can obtain the mirror image of this. It is quite here we can say this as the axis. Since it is symmetric, instead of this less than minus 0.5, we can identify it is actually it will be same for this region. It is plus 0.50. It is because we have identified that the normal distribution is symmetric around its mean. Since it is symmetric around its mean, we can say that the mirror images will be same. Therefore, instead of taking less than minus 0.5, we are saying that it is greater than 0.5. It is greater than 0.5 using the properties of the normal distribution. Therefore, now we need to identify probability that Z greater than 0.50. But if you consider about this table, the value that they are providing us is it is only for the less than, or it is for the less than or equal area only. But we are having the value now as probability that X greater than 0.5. Now we are again meeting up with the question. It is because still in this table it is given as less than. Therefore, now what we can do is using the theories of the probability, now we are trying to obtain, or we are trying to convert this into a equation with less than. Therefore, what we can do is instead of using this, if I draw it here, then here we'll get the area. It is probability X greater than 0.5. Therefore, this probability here, if it is 50, then this will be equal to probability of X less than or equal, or it is less than 0.5. But the addition of these two should be equal to 1. It is because the maximum probability that we can have for any given event is equal to 1. Therefore, using that concept, what we are going to do now is instead of using this greater than, we are trying to convert it into another form. It is now we can write it as probability. Instead of using probability X greater than 0.5, we can say it is equal to 1 minus probability X less than 0.5. You can take less than, or else you can take the less than or equal. It is because here we are not going to worry about the continuity correction. It is 50. Okay, now instead of using this greater than, we can now convert it into this quantity. Therefore, we can rewrite it as this probability of Z greater than 0.50. What we are saying is it is equal to 1 minus probability of Z less than 0.50. It is because we know that these two areas will be equal. The summation of these two areas will be added up to 1. Here you will get 0.5 here. Then you will get this quantity. And if I have this other quantity this way, therefore the probability that X less than 0.5 and the probability that X greater than 0.5 will be equal to 1. The addition will be equal to 1. That is why we can say it as probability 1 minus, this is equal to 1 minus probability of Z less than 0.5. Now we can simply read the value. We can simply read the value. Therefore, Z, what we need is Z less than 0.5. Less than 0.5. Now it is less than 0.50. Again, we are getting this value as 0.6915. Therefore, we can say this is equal to 1 minus 0.6915. Then you will get this value as here it is once you perform the calculation. It is, you are getting value as 0.3085. Therefore, you can comment on this. The probability that the employees having monthly overtime which are less than 20 hours is equal to 0.3085. In the third part of this question, it asks us to calculate what is the probability that it is more than 60. The probability that it is more than 60. Therefore, what we can do is first we are writing it. It is x, it is more than 60. First, we need to standardize it. Here it is x minus mu divided by sigma. Then we'll get it as 60 minus mu is 35 divided by sigma. It is equal to 10. It is equal to 10. X minus mu divided by sigma. Therefore, once you perform this calculation, you may get the value that probability x minus mu divided by sigma, it is Z. Now it is greater than, once you perform the calculation, you will get it as 2.5. Since we need to keep it into two decimal places, I am keeping 0 here. Therefore, we need to calculate the probability of Z greater than 2.50. Therefore, for the easiness of this having the graphical representation, it would be easier for us. Therefore, what I am drawing here is we are getting the normal distribution. Then we are having the value 0. Now we need to calculate the probability that is it greater than 2.50. 2.50, it is somewhat like here, 2.50. Now what we can do is we can again redo this alteration that we have done. The transformation, we can say it as, instead of this greater than, what we can say, it is equal to probability that Z less than 2.50. Z less than 2.50. Now we need to calculate this value or see this value from the table. If you see the value from the table, it is less than 2.50. If you see on the table, 2.5, it is somewhat here. 2.5 is here. Then we have to select this row. Then next value is 0. It is the last digit we are taking here. Last digit we are taking. Therefore, we have to use this column. Therefore, now we can see that this is the value. It is 9938. Therefore, we can say this value is equal to 0.9938. This is equal to 1 minus 0.9938. If you do this calculation, then you will get it as 0.0062. Therefore, you can say that the probability of having the overtimes greater than 60 hours per month is 0.0062. Very low probability that an employee is taking more than 60 hours as overtime per month. And as the last part of this question, it is asked us to calculate that it is in between 30 and 50 hours. It is in between 30 and 50 hours. Therefore, what we can do is it is in between 30 and 50 hours. First, we need to write it. Probability that X is in between 30 and 50 hours. First, we'll try to do the transformation. If you do the transformation, we'll get this as, here it is 30. It is less than X. It is again less than 50. Then we have to this less than 50. Then we need to have this minus mu. Then minus mu in the sense it is 35 here. It is 35 here. Then divided by sigma. It means that both sides has to be divided by 10. Therefore, we can have the value. It is that the probability that x minus mu less than sigma it is Z. Then we'll get here 50 minus 35 divided by 10. It is 1.50. 30 divided by 30 minus 35 divided by 10. It is minus 0.50. Therefore, these are the values we are getting. Then what we need to do is we need to identify what is the actual area for this. This probability of Z lies in between minus 0.5 and 1.50. Then I will, if I draw it, we'll get the standard normal distribution in this way. We are getting 0 here. Then it is in between minus 0.5. Minus 0.5 is somewhat here. Minus 0.50. And here also, again, I have kept the answers into the 2 decimal places. Then we can say the next value is 1.50 plus 1.50. Therefore, now we can have this area that we need to have the probabilities. Now we need to find out this area for the probability. Therefore, since we need to calculate this area, apart from having this this intermediate area, what we are trying to do is we try to separate this into 2 parts. First, we'll see. First, I will take the area which is less than point. If I take about this, to find out this area, I will take first. I will take it is 1.50. I will take the entire area which is the entire area which is below this 1.50. Here I can take that this is the area which is below the 1.50. We can directly read out this value from the table as well. Less than 1.50. Therefore, now if I need to take the area in between minus 0.50 and 1.50. Therefore, what I do is now if I know the value which is less than this point, if I know the value which is less than this 0.50, if you are subtracting this quantity, then what will we get is we can simply get the area that we need. This is the area that we need. It is actually in between this 0.50 and it is actually in between this in between minus 0.50 and 1.50. Since this is the area that we need to obtain, therefore instead of using this inequality, two-sided inequality, we can simply rearrange it in this form. Once we arrange it, then I will get it as probability. First, I have taken Z less than 1.50. First, I have found out this area, and then I have subtract the area which is less than minus 0.50. Therefore, this is what I have done at first. Now we'll see whether we can read out these values. Probability of Z less than 1.50. We can directly read out that value. Z less than 1.50. The value is 1.5. Value is 0. Then we can say the value is 0.9332. Therefore, for the first part, we can take the value is equal to 0.9332. But to get the value or the area which is below this minus 0.50, what we can do is, here we can see that we need to find out this area. Zero is here. We need to area. Find out the area. It is minus 0.50. But we know that previously also we have identified that the same area, if it is 0 here, then this area would be equal to the area which is greater than 0.50. Therefore, instead of this part, what we can do is now we can say that this is equal to probability of Z, it is equal to greater than 0.50. Since we have done this calculation, now we are having 9332 here minus, instead of taking this greater than, what we can do is we can rearrange this as probability of P Z less than 0.50. Now we can write this value, it is 0.9332, then it minus 1 minus probability of Z less than 0.50. Probability of Z less than 0.50, less than 0.50 value is 0.6915. Here we have get this value 0.50, 6915, 0.6915. If you solve inside the bracket, then we'll get here it is 9332 minus 0.3085. Therefore, we'll get the probability values. It is, once you solve this do this calculation, it is 7 here. It is 2, 8 with 4 here. Then 2 here, 6 here. Then we'll get this value as 0.6247. Then we can say that the probability of employee taking the overtime hours in between 30 and 50 is equal to 0.6247. And this is all what I need to discuss for this session. And thank you all for participating with this session.